Hi, welcome to this lecture. In this video, we are going to learn about the factors affecting speed. The primary factors are bandwidth and latency. But before going to understand about bandwidth and latency, let us first understand why speed is necessary. When speed is good, user engagement on your app or web increases. Secondly, it also helps in retention of your users. If the experience is good, then user will again come back to your app and will make more purchases. Thus, it will result in higher conversion. Hence, speed plays a very important role. Now let us understand what all components of speeds are. Latency and bandwidth are the major component of speed. Latency is the time from source sending a packet to destination receiving it. And bandwidth is the maximum amount of data that can be transferred on physical communication path in one go. So latency is the time taken when a data is being sent from source to destination in form of packet. So it is the total time taken by the data to reach to its destination. And bandwidth is the amount of data that can travel in one go. That means on a channel, the amount of data that can be put on the link can be measured in kbps, mbps or gbps. Thus the amount of data, for example, if you can put 50 MB data in one go, then bandwidth will be of 50 MB. So these are the two major components that plays an important role in the speed. So for example, we have a client, your device is connected with a Wi-Fi and your router providing the Wi-Fi is connected to your ISP, and then in between there are certain networks, and at the server side there is again ISP and some Ethernet cable connecting to the physical server. Thus if you send some data from client to destination, then the time taken from client to reach to destination is latency, and it is measured in milliseconds, and the amount of data that you can put in a single go is measured in Mbps, and it is known as bandwidth. In this video we are going to learn about components of latency. There can be components of latency at different level, and at router level there can be many components that can play a significant role for latency. Some of them are propagation delay. Propagation delay is the time required for a message to travel from sender to receiver, which is a function of distance over speed. Next is transmission delay. It is the time required to push all the packets bit into the link, which is a function of packets length and data rate of the link. This simply means how much time is required to put all the data packets onto the link, and this depends on the length of the packet and the data rate of the link. How much data the link can transfer in one go. This comprises of transmission delay. Next delay is processing delay. It is the time required to process packet header, check for bit level errors and determine packet's destination. So basically it is the delay that is caused by processing packet header. So every data that is being transferred have some metadata, or you can say information about that data. So that information needs to be processed, like where is the packet coming from, where is the data coming from, and where it needs to be sent, and if that packet is corrupted. So all this processing happens to check the packets, and the delay caused by these is known as processing delay. Another kind of delay is queuing delay. It is the time for which packets wait in queue until it can be processed. So as we just discussed, processing delay is happening because of processing the header of the packet. Meanwhile, the packet is getting processed, there can be a queue waiting to be processed. So it is the delay caused in the queue before the packet can be processed. This is known as queuing delay. So all these kind of delay adds latency, and all these are related to router. So total latency is equals to sum of all these delays. Please note that network data rates are calculated in bits per second, that is a small b is there, and non-network equipment use the unit bytes per second, so it's a capital B. There is a concept called buffer bloat in local router. So in router, buffer bloat is a situation causing delay or undesirable latency by buffering excess amount of packets in queue. So router can buffer a lot of amount of packets in queue, and it can lead to a situation where this is causing unnecessary delay, and this situation is known as buffer bloat. In this lecture, we are going to understand speed of light and propagation latency. Speed of light is 299,792,458 meter per second, and speed of light depends upon medium, which means there is a hard limit. Speed of light depends on the medium in which it travels. This means there is a limit to it. So for example, if the route is from New York to San Francisco and the distance is approximately 4000 km, then the time taken by light in vacuum would be 14 milliseconds. So this is very low and it is in vacuum, and if it travels in fiber, then it would be 21 milliseconds. And nowadays we are using fiber optics cable, thus we will incur latency of 21 milliseconds. And the round trip time is the time for a request to go and the response to come. So it will be a round trip time. That means client sending a packet to server and then server responding with some data. So this is like going and coming back. This is known as round trip time, RTT. So in fiber, the RTT would be 42 milliseconds. And if you are sending the same data over a distance 5500 km, then it will incur us 28 milliseconds of latency in fiber, and the RTT would be 56 milliseconds. And similarly, if the data is traveling a lot like 40,000 km, then the time would be 200 milliseconds. Thus we see the more the distance data is traveling, the more the latency is getting add up. Let us understand about last mile latency. It is often the last few miles and not the in-between distance that causes the latency. This means ISP could be causing or adding more delay, so one should check for better ISPs. ISPs are nothing but your internet service provider, and this can be checked with traceroute command. So if in terminal you put traceroute google.com, then this will show this kind of output, and here as you can see the line number 1, this is the first hop, that is local wireless router. This is your router, and if you see the 11th one, this is the 11th hop and this is Google server. Let us try this command. So as you can see, the first one is my router, and here as you can see it is almost going to 2 milliseconds, and till the 4th hop this is my ISP, Airtel broadband.in. So out of 11 till 5th hop it is my ISP that is incurring the latency, and if you see till here it is coming out to be somewhere around 13 milliseconds out of 30. So to reach at the final destination it is taking 30 milliseconds, and here as you can see out of that 13 milliseconds is just from my local ISP. Thus the last mile latency can be causing a lot of delay, so it is better to check and choose the right ISP. Hi, welcome to this lecture. In this video we are going to learn about TCP. TCP is one of the main protocol of internet. TCP is also known as TCP IP protocol. There are two protocols which are known as main protocol of the internet. One of them is IP, that is Internet Protocol. It is a method or protocol by which data is sent from one computer to another over internet. Another one is TCP, that is Transmission Control Protocol. It provides reliable transmission of data over unreliable network. So together TCP IP is known as Internet Protocol Suite. So every connection you are making over internet, if you are accessing a website, then every time a TCP connection is being made. Hence TCP IP is sort of backbone of the whole internet. Let us see what TCP IP protocol do. Whenever you are trying to access a website or application, there is a three-way handshake that is taking place. That three-way handshake is nothing but a TCP connection that is being created. All TCP connection starts with a three-way handshake. Before sending or receiving any data, the client and the server must complete three-way handshake. Then only they can transfer the actual data. There are certain steps that is involved when a three-way handshake takes place. Those steps are: client picks up a number X and sends a SYN packet. We are calling this packet as a SYN packet, and the client is picking up a number x randomly. Syn ec. Server receives the syn packet and server increments the number x by 1 and chooses another number y, sends a syn ec packet. Once this is done, the client receives the syn ec packet and then it increments both x and y and complete the packet by sending ec packet. Let us see the visual representation of this whole TCP handshake. So as you can see, on the left hand side we have a sender and on the right hand side we have a receiver. The sender is sending a syn packet and choosing a number x, and it is a random number. So at 0 milliseconds the syn packet is being sent and it takes 28 milliseconds for this packet to reach to destination. The receiver receives the syn packet and increments the number x by 1 and chooses another number y, and this number is also random, and then it sends a syn ec packet. This syn ec packet is received by sender at 56 milliseconds and then it increments both the number and sends out an ec packet. Now along with this ec packet it can also choose to send application data. This whole communication is known as three-way handshake, and this is a must whenever a connection is taking place between sender and receiver. So the takeaway from three-way handshake is a three-way handshake can be expensive because it is incurring some latency. As you can see, while transferring this syn ec and ec packets, it is taking some time. This is causing some delay. So every time a three-way handshake makes a new TCP connection, it is expensive. Hence, TCP connection reuse is a critical optimization for any application running over TCP. Hence, if the application is using TCP, try to reuse existing TCP connection instead of making a new one every time. Let us now understand a concept called TCP fast open. When a web page is loaded, it can fetch resources from dozens of sources. Each of these sources will require to open new TCP connections. Each of these TCP connections will increase latency, and to eliminate or reduce this expensive latency, TFO was introduced. TFO stands for TCP fast open. Let us try to understand how a web page can try to fetch resources from other sources. For example, if I open a browser and if I simply open amazon.in, and then we can inspect this and go to network tab, and let us try to refresh the page. So as you can see, these are the domain it is trying to access. One is amazon.in, and then there are subdomains from amazon.com or from certain CDNs or other sources like www.imdb.com. These are different sources from which it is trying to load resources. Thus it is making TCP connection with all these sources. So TFO is a mechanism to eliminate latency penalty imposed on new TCP connection by allowing data transfer with SYN packet. So if you remember, the SYN packet was not transferring any data. The application data was being transferred with the ec packet or maybe after that. So TCP fast open is allowing to send data when a SYN packet is sent. TFO has its own limitation. It is limited to the size of SYN packet. Since we are just trying to make use of SYN packet and the SYN packet size is limited, we cannot send data beyond the size of SYN packet because SYN packet will have its own data. However, this will help us to improve the speed significantly. In this video, we are going to understand the concept of congestion avoidance and control. Before that, we need to understand what is congestion collapse. So whenever IP gateways are connected to network of widely different bandwidth, packets coming to it will be in queue, and when RTT exceeds to maximum, IP gateway will receive extra some copies of same packet. This will worsen the network with congestion. This simply means the source is sending packets or data and the destination or any hops in between will receive the packets, and if the RTT times exceed to its maximum, that means the time within which it was supposed to respond or process it exceeds. In that case, another copy of the same data will be sent assuming that the previous one was lost. This will result in sending same copies of same data again and again, and this will simply congest the network, and this situation is known as congestion collapse. To address this problem, various mechanism has been implemented. There are certain methods to handle congestion collapse. One is flow control, second is congestion control, and third is congestion avoidance. Let us understand what is flow control. It is a mechanism to prevent sender and receiver from overwhelming the receiver with the data. So basically, sender and receivers are restricting the data they are sending or receiving from flooding each other with the data. So sender and receiver advertises their receiving window, in short it is RWND, and each ACK packet will carry latest RWND value so that receiver will know how much to send. So as we discussed, the three-way handshake, that is TCP connection, SYN, SYN-ACK and ACK package are being transferred with the help of flow control. What we are doing is, with ACK packet we are sending RWND size. It is the size that it can receive at that particular moment, so that whenever the sender is sending the data, it will not overflow the data, and it will only send the data that is acceptable by the receiver at that particular moment. So here we are controlling the flow from sender and receiver both sides, and both of them are advertising or publishing their RWND size. That means the amount of data they can handle at that moment. In this way, they are helping each other not to flood or congest the network. This is flow control. Another concept is window scaling. So initially RWND size was of 16-bit. This imposed a hard upper limit, that is the max value could be 2 to the power 16 or 65535 bytes. You must have seen this number in Linux in hard limit and soft limit. So this is what the number is. In RFC 1323, TCP window scaling option was introduced. This allowed to raise RWND size from 65535 bytes to 1 GB. On Linux, window scaling option can be checked with following command: sysctl.net.ipv4.tcp_window_scaling. In this demo, we are going to see how we can check window scaling option in Linux. So these are the commands which you can use: sysctl.net.ipv4.tcp_window_scaling. This will output a value equals to 1. If its value is 1, it means it is enabled, and if its value is not 1, that is 0, then it is disabled. So this is one optimization that you can do in your Linux server. So let us go ahead and see how we can do this. So here I am on one of the Linux based server. So this is the sysctl command. Let's run it. As you can see, the output of this command is 1. That means this option is already set to 1. This simply means window scaling is enabled. You can set this using the command sysctl-wnet.ipv4.tcp_window_scaling equals to 1. So let us go ahead and try to set it. And as you can see, it is set to 1, although it was already set, but I am just demonstrating the command. This is a temporary setup. If you want to do this permanently, you need to edit a file. That file is under proc sys-net-ipv4 TCP window scaling. If we get this file, we see the value is set to 1. We see the value is set to 1. That means window scaling is enabled now. So this is it for this demonstration. See you in the next video. In this video, we are going to learn about slow start. So as we have seen, despite of flow control, network congestion collapse was a big issue. Flow control prevented sender from overwhelming the receiver, but there was no mechanism to prevent overwhelming underlying network from other side. To understand this scenario, let us take an example. There is a user who is watching a movie, and this is the server. Depending on the bandwidth, maximum video quality achieved. So whatever the bandwidth available over this line, the quality of video will depend on it. Now suppose there are two users watching a movie from a server, and here two users are in the same network, but channel is distributed. Here the data server adjusts the data rate, otherwise if it continues at the same rate, the data will pile up and packets will be dropped. This will lead to inefficient use of network. So to avoid this scenario, we have something called congestion window size, which is also known as CWND. So in CWND, there is a limit on amount of data the sender can have in flight before receiving an acknowledgement from client. Let us understand this scenario with an example. So client is in New York and the server is in London. Then three-way handshake is performed, during which both sides advertises their respective receiving window size within egg packets. Once the final egg packet is put on wire, we can start exchanging application data. Only way to estimate the available capacity between client and server is to measure it by exchanging data. This is what slow start is designed to do so. To start, server initializes a new congestion window variable per TCP connection and sets its initial value to a conservative system specified value, which is known as init CWND on Linux. So server is setting up variable CWND, and this is an initial value, and it picks up this value from system specified value which it can find in Linux using init CWND. Now the question is, how CWND value or size is determined? The solution to identify it is to start slow and grow the window size as the packets are acknowledged. This is what slow start means. So initially the server will set some value and it will be a conservative value, and with its acknowledgement packet it will send that value to the client, and when client receives it, it will start sending data based on that value, and in the subsequent acknowledgement packet from server side it can increase the CWND value depending on the network. So originally CWND value starts with one network segment. Now here we don't need to go much deeper into what a segment specify, but we can consider it as a small unit of a network. So CWND value starts with one network segment initially. In 1999, CWND value was updated to 4 network segment because one network segment was slow. So in 1999 it was updated to 4 network segment, and in 2013 it was updated to 10 network segment. So maximum amount of data in flight for new TCP connection is the minimum number of RWND and CWND values. Hence a modern server can send up to 10 network segments to the client, at which point it must stop and wait for an acknowledgement. Then for every egg received, the slow start algorithm indicates that server can increment its CWND size by one segment. This way the client and server are trying to quickly converge onto available bandwidth on network path between them. So in simple words, this is like when you are watching a movie, so the server can start streaming with low quality video, and based on the acknowledgement it receives from client that its receive window size is higher and its receive window size says like I am able to take more packets, then the server can increment the CWND value and will start sending more packets, and it can gradually increase the quality of the video. At some point of time it will start streaming at the maximum available bandwidth. This way it is not overwhelming the network and it is not making the network congested, and it is efficiently using network bandwidth. I hope you now have a better understanding of what a slow start is. If not, we are going to spend a bit of more time on slow start example. The client and server receives windows 65535 bytes, that is 64 KB. Initial congestion window is 10 segment, and a round trip time 56 millisecond considering location to be London and New York. So one segment is equals to 65535 per 45 bytes. So one segment will be equals to 1460 bytes. Round trip time is 56 millisecond. Client and server bandwidth is 5 Mbps. Client and server receive window size 65535 bytes. Initial congestion window 10 segments is equals to 10 into 1460 bytes equals to 14 KB. So server processing time to generate response is 40 millisecond. No packet loss egg per packet. So these are the given details that we have, and we have certain assumptions here. And as you can see, one segment is equals to 1460 bytes. and as we know, initial congestion window is 10 segments. So initially it can send up to 14 kb. Now let us see this with a diagram. So at 0 millisecond, client begins the TCP handshake with a SYN packet, and at 28 milliseconds the SYN packet is acknowledged, and at 56 millisecond acknowledges SYN ACK packet and specifies its RWND size, that is receive window size, and immediately sends an HTTP GET request. So here as you can see, it is making a GET request at 56 millisecond. This GET file request is received by the server at 84 milliseconds. Now it will take some time in processing, and it will generate a 64 kb response and sends 10 TCP segments before pausing for an ACK. So it is generating a 64 kb response and it can send 10 TCP segments at a time. So at 152 millisecond, the client receives 10 TCP segments and it acknowledges each one of them. And at 180 millisecond, server increments its CWND size for each acknowledgement and send 20 TCP segments. So at first it is sending 10 TCP segments and the client is sending acknowledgement for each one, and on receiving acknowledgement the server will increment CWND for each acknowledgement, and this time it will send 20 TCP segment. 208 millisecond, client receives those 20 TCP segment and sends acknowledgement for each one of them. At 236 millisecond, server increments its CWND size for each acknowledgement it has received from client. Client receives remaining 15 TCP segments and acknowledgement each one of them, and this way the data transfer is complete. On every acknowledgement, the idea here is the server is starting with 10 segments at a time, and upon receiving acknowledgement of each segment it has delivered, it will increment the segments in the next data transfer. This way it will be able to achieve and utilize maximum available bandwidth in the network. I hope this example helps you to understand what a slow start is. In the previous example we have seen it took 264 milliseconds to transfer 64 kb file, and it was a new TCP connection. Suppose if we are using this connection again, so the TCP handshake and first transfer of the file has already happened, and now we are trying to fetch another file over the same connection. In that case, we will have some improvement over the connection and we will be able to utilize the full network bandwidth start from the beginning of the second request. So at 0 millisecond, client sends HTTP request, and at 28 milliseconds server receives HTTP request. At 68 milliseconds, server completes generating 64 kb response, but the CWND size this time is already greater because it was already set high because of previous file transfer. Hence this time it will send all those 15 segments in one go. At 96 millisecond, client receives all 15 segments and sends acknowledgement for each one of them. So here reusing a TCP connection gives 275% improvement in performance. So this is another parameter for optimization, that is connection reuse. We will see in upcoming lectures how and we can implement it. In this video we are going to understand about congestion avoidance. So we have seen slow start initializes the connection with a conservative value. It picks up a system specified initial value, and for every round trip it doubles the amount of data in flight until it 1 exceeds the receiver's flow control window, or a system configured congestion threshold is reached, or until a packet is lost. So on every round trip or on every acknowledgement, it will double the amount of data it is about to send, and it will keep on doing so until either of these three conditions are met. One condition is if it exceeds the receiver's flow control window, or if the threshold is reached, or a packet is lost. So either of these values will be an indicator to stop the sender from doubling the amount of data in flight. So at any point of above, congestion avoidance algorithms takes over. When packet loss happens, it simply indicates congestion, and the algorithm is used to decrease or configure the CWND. So as you can see on the left hand side we have congestion window, and here on the x-axis we have number of transmission. So initially it is starting with a slow start, and as soon as a packet loss happens, it indicates congestion and it will lower down its CWND size, and then it again start sending the packets, and on acknowledgement it will start increasing the CWND size. If the threshold is met, it will incrementally start increasing the congestion window, and it will keep on incrementing until a packet loss happens. If a packet loss happens, it may configure the threshold to be a bit lower than the previous one. The packets, it will start increasing their CWND size. So this is how congestion avoidance algorithm works. Hope this video was useful. See you in the next one. In this lecture, we are going to understand about bandwidth delay product. Bandwidth delay product is the product of data link's capacity and its round trip delay time. In short, it is known as BDP, and it is equals to data link capacity multiplied by round trip time delay. This is equivalent to the maximum amount of data in network at any given point of time. So this simply signifies what is the maximum amount of data in a network at any given point of time. That is the maximum amount of data on network without acknowledgement. So network with large BDP is called long fat network. Hi, welcome back. As you might know, HTTP2 is already in practice and is improving the speed of your web application a lot. But before that, it was HTTP1, and HTTP1 still being used by many web applications. So in this lecture, let us go ahead and see what is HTTP1 and what all features it have and what are its limitations. As you all know, all web application works over HTTP. HTTP stands for Hypertext Transfer Protocol, and it is one of the major protocol that is being used. So before HTTP1, it was HTTP 0.9, and there was certain limitation in HTTP 0.9. So there was a need of a protocol that could serve more than just hypertext documents and provide richer metadata about the request and response. Here are some capabilities of HTTP1. The request may consist of multiple new line separate header fields. Response object is prefixed with a response status line. Response object has its own set of new line separated header fields. Response object is not limited to just hypertext. The connection between server and client is closed after every request. Here are some of its limitations. Per connection, there could be one request and response. So you cannot have multiple request and response within the same connection. Host header is optional. Limited support for caching. After that, due to these limitations, the HTTP was continuously evolving, and due to the limitation we just discussed, HTTP 1.1 was introduced. It became an internet standard soon, and as of now also HTTP 2 is not adopted everywhere. By default, HTTP 1.1 is working. So there was a need to improve HTTP performance, and HTTP 1.1 was designed to majorly focus on performance. Here are the capabilities of HTTP 1.1. It can have persistent connections to allow connection reuse. That means the same connection can be used for multiple requests, and it is persistent. The request pipelining to allow parallel request processing. That means multiple requests can be sent together for parallel processing. Chunked transfer encoding to allow response streaming. Byte serving to allow range-based resource request. Improved and much better specific caching mechanism. Although it has all these features, but there were certain limitations, such as HTTP 1.1 is very sensitive to connections with high latency, single request response at a time. Browsers use multiple connections to achieve concurrent requests and responses. Requests and responses are verbose, text-based, many headers. Now the question is, why we need HTTP 1.1? Because it gave us caching, hierarchical proxy support, persistent connections, virtual host support, authentication, issue with increasing size of content. So due to these factors, HTTP 1.1 was the need of our... Hi, welcome to this lecture. In this video, I am going to talk about keep alive connection, which is one of the most important concepts when we talk about TCP connections. So if there is only one TCP connection and we need to fetch two resources or less than 4 KB, each TCP connection begins with TCP handshake. So for the HTML file and CSS file, TCP handshake will occur and both will take the same amount of time. Replace all this with single TCP handshake so there is constant time for making connection, and other will depend on the size of resource. The benefit of this is reduction in time, and we save more time, and the same connection can fetch us multiple files, and it will reduce the overhead of doing the TCP handshake again and again. For example, here in this case, we have a client and we have a server. So first we are having a TCP handshake. So till here 56 millisecond we are doing the three-way handshake. A SYN packet is sent, SYN is acknowledged, and then acknowledgement is being sent, and after that we are fetching the HTML file with a GET request, and then it gets processed in 40 millisecond, and then there is a HTML response. Then there is again a GET request for CSS file, and it is being processed in 20 millisecond, and then the response is being sent and the connection closes. So as you can see here, we are using the same TCP connection. That means the SYN packet and its acknowledgement is not happening for CSS request. So this TCP handshake is not happening again, and we are saving this 28 milliseconds of time to get this CSS file for the second request. Hi, in this lecture we are going to discuss about HTTP pipelining. This is also a very important concept that you should know. So when a request is being sent or it is being served, it is generally in FIFO, first in first out. So what HTTP pipelining does is it allows us to reuse an existing connection between multiple application requests. It follows FIFO order to respond to request. It keeps the server busy by processing the request. With HTTP pipelining, they eliminated another network round trip in between requests. Parallel request processes on the server. When we send two requests A and B, A will go first. So if A takes 40 milliseconds of time and B takes 20 milliseconds of time, then B have to wait for A to complete processing, because request A came first, so B will be stored in buffer and then cleared. The limitation of this is buffer will be used. So without pipelining, we have a client and a server. The connection is being open, a request is being sent, and then its response is given, and then another request is issued. So here with no pipelining, we are sending each request only after receiving the response of the previous one. With pipelining, what we are actually doing is, after opening the connection, we are requesting a resource, and then without waiting for its response, we are sending out another request for another resource, and so on. As you can see, these three requests are getting served in almost half of the time as it was happening without pipelining. So it is saving a lot of time for us. Hi, in this lecture, we will talk about multiple TCP connections. The client can dispatch up to 6 requests in parallel. Server can process up to 6 requests in parallel. The cumulative number of packets that can be sent in the first round trip is increased by a factor of 6. And it is being done by CWND that we have already discussed. The maximum request parallelism in absence of pipelining is same as number of open connection. The limitations are additional socket consuming resources on client, server, and all intermediate hops, so they require extra memory buffers and CPU overhead. Competition for shared bandwidth between parallel TCP streams, because if request and response are traveling in parallel, they will consume some bandwidth. Much higher implementation complexity for handling and collections of socket. Limited application parallelism even in light of parallel TCP streams. Hi, let us now discuss about domain sharding. So when we open a web browser, all the resources that are being downloaded are generally from the same domain. For example, if you are accessing example.com, which is your website, then generally all images, CSS file, JavaScript file will be hosted on the same server, and the request for these files will go to the same server. As you know, there can be limited parallel connection opened for a particular domain. To overcome this limitation, web developers move to some content to multiple subdomains. This is known as domain sharding. So the resources can be distributed to multiple subdomains. Number of browsers can connect with multiple servers, domains or subdomains simultaneously by opening TCP connections. The benefit of this is it helps in serving multiple concurrent requests, but the limitation here is it adds to the complexity of development, deployment, and maintenance of overall cost to application. Concatenation and spreading. Concatenation is multiple JavaScript or CSS file are combined in single resource. So for example, if you have multiple JavaScript file or CSS file, then a request for each file can be costly, as to request all those files there will be a separate request and separate response for it. But if you have multiple JavaScript, then during deployment you can combine all the JavaScript code into a single file and you can minify it so that whenever the request is made, it can be made for a single JavaScript file or CSS file, and you will get all of your JavaScript code within a single request. Splitting. Multiple images are combined into a larger composite image. So this is just like concatenation, but it is being done for images rather than JavaScript or text-based files. The benefit of these are it reduces protocol overhead by combining file into a single resource. Application layer pipelining. That means data from multiple responses is streamed back to back, eliminating extra network latency. There are more limitations to it. Consider the not unusual case of an application with a few dozen individual JavaScript and CSS files, all combined into two requests in a production environment, one for the CSS and one for the JavaScript assets. In this scenario, all resources of same type will live under the same URL and cache key. Combined bundle may contain resources that are not required for the current page. So you will be wasting sending extra data or extra code. A single update to any one individual file will require invalidating and downloading the full asset bundle again. This will result in high byte overhead cost. Both JavaScript and CSS are parsed and executed only when the transfer is finished, potentially delaying the execution speed of your application. This is it for this lecture. See you in the next one. Hi, we have already seen what is HTTP1 and what were its benefits and limitations. Now let us move to HTTP2. In this particular video, I will talk about what is HTTP2 and what are its benefits, but we have a separate demo using Nginx in the coming videos. The primary goal of HTTP2 are to reduce latency by enabling full request and response multiplexing, minimize protocol overhead via efficient compression of HTTP header fields, and add support for request prioritization and server push. To implement these requirements, there is a large supporting case of other protocol enhancement such as new flow control, error handling, and upgrade mechanisms. But these are most important features that every web developer should understand and leverage in their applications. HTTP does not modify the application semantic of HTTP in any way. All the core concepts such as HTTP methods, status code, URIs, header fields, etc. remains in place. Instead, HTTP2 modifies how data is formatted or framed and transported between client and server. So as a result of this, all existing applications can be delivered without modification. So you don't need to modify anything at application level and you can leverage HTTP2 benefits. Hi, in this video, I will talk about binary framing layer. So at the core of performance enhancement of HTTP2, it is the new binary framing layer which dictates how HTTP messages are encapsulated and transferred between client and server. So at application layer, it is the binary framing. The framing looks like this. Previously it was this HTTP1 and this is how it was. For example, a post request with /upload and it was using HTTP1 and host and other headers were there and there was a message. Now in the new framing, the headers frame is separated out and then there is a data frame which contains the message. Unlike the new delimited plain text HTTP1 protocol, all HTTP2 communication is split into smaller messages and frames, each of which is encoded in binary format. As a result, both client and server must use the new binary encoding mechanism to understand each other. HTTP1 client will not understand an HTTP2 only server, and vice versa. Thankfully to the design, our applications can remain unaware of any of these changes as the client and server perform all the necessary framing work on our behalf. So this is all for binary framing layer. Hi, in this lecture I will talk about streams, messages and frames based out of HTTP2. The introduction of this new binary framing mechanism changes how the data is exchanged between client and server. And to understand this, there were new terminologies that were introduced. One is stream. So stream is a bidirectional flow of bytes within an established connection which may carry one or more messages. A message is a complete sequence of frames that map to a logical request or response. A frame is the smallest unit of communication in HTTP2, each containing a frame header which at a minimum identifies the stream to which the frame belongs to. So all communication is performed over single TCP connection that can carry any number of bidirectional stream. So this is all about HTTP2, and we have a demo in the upcoming videos where I'll be explaining how to enable HTTP2 and Nginx and what all benefits we get using HTTP2. So far we have learned a lot about TCP. Now it's time to look and summarize what all things we can optimize for TCP. So optimization for TCP revolves around core concepts that we have seen. TCP three-way handshake introduces a full round trip of latency. TCP slow start is supplied to every new connection. TCP flow control and congestion control regulate throughput of all connection. TCP throughput is required by current congestion window size CWND. So based on these things, we will see what we can optimize for TCP. Let us see what we can optimize or tune at server configuration level. So we can tune specific values of each buffer and timeout variable. To tune a server, tuning specific values of each buffer and timeout variable could be complex as a starting point. So what you can do is, the easiest way would be to start optimizing is to upgrade host system version. This simply means to start upgrading kernel version. So we have upgraded kernel. What's next now? Once we have latest kernel in place, you can now configure the server with the following best practices. Increasing TCP's initial congestion window. So we have seen initial congestion window CWND size was set to 10 segment. We can increase it. So you can go ahead and increase it if network bandwidth can support more data. So go ahead and increase it. Slow start restart. After idle time in connection reuse, slow start should be disabled. In short, slow start should be disabled for long-lived TCP connection. If your TCP connection is a long connection, then the slow start should be disabled, because if you try to access another file within same TCP connection, then it should not start slow. It should make use of the maximum CWND size available. For window scaling, increase the RWND size and make use of TCP fast open, that is TFO. Send data along with initial sync packet. To tune application behavior, you can use the following points. Send fewer bits, send data which is required. Do not send extra data which is not required. We cannot make the bits travel faster, but we can move the bit closer. That is, you can compress the data that you want to send. Reuse TCP connection, because we have seen a new TCP connection will start slow and the segment size would be low. The SYN packet and its acknowledgement will again take time. It is better if the three-way handshake is already done and you can make use of the same connection for multiple transfers. Try to use CDN to reduce latency. CDN is nothing but content delivery network. There are CDN servers that are spread across the globe. So any cloud provider, for example AWS or Google Cloud, will have its CDN server across the globe, and the CDN server caches the most frequent access data. It can cache sudden images or static data that you want to cache. So a person residing near to that location doesn't need to go to the server to get the file if the same file is available at the nearby CDN server. This will help you to reduce latency. So based on this, we have certain checklist. So studying above concepts and things, we have a performance checklist. The checklist is as follows: upgrade server kernel version to the latest version, ensure CWND size is set to 10, ensure that the window scaling is enabled, disable slow start after idle, investigate enabling TCP fast open, eliminate redundant data transfer, compress transfer data, position server closer to the user to reduce round trip times, reuse TCP connection wherever possible, investigate TCP tuning for HTTP recommendation. So this is all about this video. See you in the next one. Hi. So far we have seen the concepts related to network performance. Now in this video we are going to discuss some parameters that you can tune to enhance network performance in Linux. So before going to deep dive into those parameters, let us understand about sockets. So sockets allow communication between two different processes on the same or different machine, or to be precise, it's a way to talk to other computers using standard Unix file descriptor. In Unix, every I/O action is done by writing or reading a file descriptor. A file descriptor is just an integer associated with an open file, and it can be a network connection, a text file, a terminal, or something else. A socket is bound to a port number so that TCP layer can identify the application that the data is destined to be sent to. When two applications interacts with each other within same network or different network, it opens up a socket, and there is a SK buffer, or which you can say socket buffer, and when the packet is ready to be transferred, it is transferred to the network interface controller, send it over network, and at the receiving end it is received by the NIC. Now when a packet is received, it generates an interrupt. If it is a hard interrupt, then it is very costly because it will result into context switching, and context switching is giving the control of the CPU to another process by saving state of current process. So this is context switching, and it is a very costly phenomena, which is why it generates soft interrupt and saves the incoming packet to a buffer. This will allow us not to have context switching too frequently. So both sides have their own buffer that we are going to discuss and see those parameters in the coming videos. So the important thing here to note is about the socket buffers. Kernel uses buffer to send and receive data. Default max value of socket buffer is set to very low because the memory you will use for this buffer, that much memory will be occupied in the RAM. So it is not good to occupy that much memory in advance. So kernel saves it to a low value, and then it automatically adjusts the size based on utilization. So by default, kernel set the value to 128 KB, and setting this value to too high will cause buffer bloat. And buffer bloat is a situation which will result in high latency and jitter in packet switched networks because it is buffering excess amount of packets. It is not also desirable to set the value to too high, otherwise it will have the issue of buffer bloat. Hi, in this video I will show you certain TCP related parameters that you can tune or change depending on the requirement, and where you can find these tunables. Increasing these values for system will help the system to handle more packets. So let us understand all of them one by one. One is TCP_mem. The parameter TCP_mem is the amount of memory in 4096 byte pages totaled across all TCP application. It contains three numbers: the minimum, pressure, and the maximum. So I am on a Linux server. To find TCP_mem, just run this command and it will show you the values. The first one we are discussing as of now, TCP_mem. So this is TCP_mem is system-wide setting for your TCP packets. Similarly, we have this for UDP packets as well. So if you run the command sysctl -a grep I UDP grep -i mem, we might need to run this with sudo command. So run the command sudo sysctl -a grep -i UDP grep -i mem, and this will show you the system wide UDP settings. This also have the minimum, threshold, and the maximum number. The UDP RMAM specify the receiving buffer and the WMAM specify the writing buffer. So as you can see, it has the value 4096, so you can change it and set it to according to your need. There is no specific value which can be a thumb rule for all your requirement, but what you can do is you can start off with some value and run some test and accordingly see the result and see the improvement and then decide which values fit best for you. At the end, I'll be sharing with you some best practices around how to tune or how to do performance tuning. I'll share some steps that you can follow for performance tuning. It will be a method to follow to come to a particular number. And similarly, we have this for TCP. So you can run the same command and just for TCP, and it will show you the TCP memory system wide and then TCP RMAM, which is the receiving size, and then TCP WMAM, which is the send buffer. So as you can see, it has three values: the minimum, the pressure, and the maximum. The pressure is the threshold at which TCP will start to reclaim buffer memory to move memory use down towards the minimum. And please note that the amount of memory mentioned here is in 4096 byte pages. This is pages. And as per IBM's high performance computing page, the recommended values are 4096, 87380 and 16777 to 16. Then for TCP mem, set it to twice the maximum value for TCP read or write multiplied by maximum number of running network application divided by 4096 bytes per page. You can increase RMAM max and WMAM max so that they can at least as large as the third value of TCP RMAM and TCP WMAM. Calculate the bandwidth delay product. So bandwidth delay product is the total amount of data in transit on the wire, and it can be expressed as the product of bandwidth in bytes per second multiplied by the round trip delay time in seconds. So 1 Gbps LAN with 2 millisecond round trip delay means 125 megabytes per second times 0.002 seconds or simply 250 kilobytes. If you don't have buffers this large on the host, senders have to stop sending and wait for an acknowledgement, meaning that network pipe isn't kept full, we are not using the full bandwidth. Then increase the buffer size as the bandwidth delay product. However, be careful. The bandwidth delay product is the ideal, although you can't really measure how it fluctuates. If you provide buffers significantly larger than bandwidth delay product for connections outbound from your network edge, you are just contributing to buffer congestion across the internet without making things any faster for yourself. Hi. In the previous video, we have seen some tunables related to TCP, and we also see what is bandwidth delay product. And in this video, I'll show you how to calculate bandwidth. That means how much data you can put in transit and accordingly set the buffer. So this is one of my hosts, and I'm just pinging another host from here. So this will give me round trip time because I want round trip time for bandwidth delay product. And as you can see, the second value is in average and this is 1.50 and it is in milliseconds. So I will use ETH tool. If you run ifconfig, we will get the NIC, and if you run ETH tool over that NIC, that is ETH2, it will show me the speed, that is 100 MB per second. Now we have this. In this video, we are going to learn about head of line blocking. Suppose we have P1, P2 and P3 packets that were transmitted from sender to receiver, and if P1 is lost, so you can also see this in diagram, 3 packets were sent from sender to receiver and the sender receives P2 and P3 and P1 got lost. So P2, P3 will be kept in buffer until P1 is retransmitted from sender. This is the buffer in gray color, and here P2 and P3 are kept in it, and this will acknowledge, the receiver will send 2 acknowledgement for 2 packets, and then the TCP retransmit happens and it will again send the P1 packet. So in this scenario, the application is waiting to read data from P1, P2, P3. So the application waits some time to read the data from these packets and it sees a delay. This effect is known as head of line blocking. Hi, I will quickly show you how to install Nginx on an AWS EC2 instance. This is a quick demo. If you are already familiar with installation of Nginx, then feel free to skip this video. So let's get started. First of all, you need to log into your AWS account and select a region. In this case, I have selected US East 1. Then go to EC2. Here, click on Instances. Click on Launch Instance button. And then you need to give a name to your instance. I'm calling it as webserver. Then you need to select a base image. So I'm selecting Ubuntu based image. So it's Ubuntu Server 22.04 LTS version. And then I'm choosing instance type t2.micro because it's free tier eligible and we will not incur any cost. Then click on create key pair, and here we will create a key pair. This key pair will be helpful to log in into EC2 instance using SSH. So just give it a name, and this will be of .pem format. Just click on create key pair. This will download the PEM file. Now on the other settings, allow SSH connection and HTTPS traffic because we will be accessing Nginx over HTTP and HTTPS. Click on launch instance. Now the instance is launching and it has launched successfully. This is the instance ID. Click on the ID and this will open up the instance details. So this is our instance. As you can see, the state is pending. So it's in creation mode. It's still creating it. Let us refresh this and it's in initializing state now. Let us refresh it again. Okay, now it's ready. The status checks are passing. We can connect through this connect button. Click on this and this is the public IP we have got and the username is Ubuntu. And if you click on connect, we will be able to SSH through browser. So let us click on this. So we have successfully logged into our Ubuntu instance. Now we will install Nginx using the command sudo apt-get update. So this will update the package list and then we will install Nginx. Once this is done, run the command sudo apt-get install Nginx. Type Y and hit enter. Okay, so Nginx is installed now. Let us check if it is already running. Run the command ps-ox grep nginx, and as you can see, it's running now. And it must be serving a default Nginx page which we can access over the public IP of this instance. So copy the public IP and then just put it in the browser, and since we have allowed HTTP traffic, so we would be able to access the default Nginx page. So this is it for this video. I hope your Nginx installation is done, and in the coming lectures we will see how we can configure and set up Nginx for better performance. Hi. Welcome to this lecture. In this video, we are going to learn about expires header for Nginx. This header can help you to optimize Nginx performance, and ultimately it will help you to have good performance for your application. So let us see how it works. First of all, you need to understand what expires headers is. So when a client sends a request and asks for a resource from server, for example, if a client, that is your browser, is requesting a server for an image, then the server responds and sends back the image to client, and it attaches some headers known as response header. Within those headers, you have a header called expires. Expires headers ultimately tells the client for how long it can cache that particular resource. So if you have specified a particular resource or a particular image can be cached for 5 days, then the client, that is your browser, will cache that image for that particular duration. This way, on subsequent request, the server doesn't need to send back that image again, and the client, that is your browser, can use the image from its cache. So this way, in subsequent requests, the performance of your application will be much better than before. So let's see this in action. I have a web server Nginx set up on an AWS instance. This is my instance on AWS, and using EC2 Instance Connect, I am logged in to my instance. Here I have already installed Nginx and it is running. So this is the Nginx process which is running, and if I access the public IP of this instance, I will get the default Nginx page. Here this Nginx page is getting served from this default configuration file. If I edit this, you can see that the server is listening on port 80 and it is serving from this particular directory where www.html. So this is the default file that it is using. We will try to add expires header. So within this configuration, what I'll do is I will add a location block equals to / python.png. So python.png is a file which is already present under where www.html folder. I will just show you. And within this location block, I am adding a header, calling it my header and giving it a value test header. Let's save this file. Now this is reloaded. To test this out, all we need to do is we need to make a curl request with -i option, and we can use the same parameter. We can use the IP, and at the end we will say python.png because we have specified header for this particular file. So it has responded with all the headers, response header. So this is a 200 OK response and it is being served through Nginx. And as you can see, it has added a header, my header, and with a value test header. If I do same for the default page, then I will not get this header because the default page, the default index HTML page doesn't have this header because we have specified this for this particular file, python.png. You can also check this through browser. If I try to access python.png, so this is the image, and if you inspect the page and go to network tab and just try to hard refresh this page. So for python.png, in the header section you will have response header here, and the header my header is added. So you can test this here as well. Now we will try to add cache and expires directive. So let's go back in the configuration file and let us go back to the same section, and here apart from this header, what we are going to do is we are going to add more headers. So let us add header and add cache control and set it to public. That means this resource can be cached publicly. Then add another header called pragma and sets the value to public. This is just the older version of cache control. Then add one more header vary and set it to about the vary except encoding. We will discuss this in the upcoming lecture. Finally, we will set the expires directive and will set it to 60M. That means 60 minutes. You can also set it to 1 capital M. Capital M is for month. Here this will be 1 month, or you can set it for 1H, that is 1 hour. So depending on the time duration you want to cache this particular resource, you can add the expires directive. Let us go ahead and save this and then reload the Nginx. Then let us make the curl request again for python.png. And as you can see, this time along with my header you have cache control public, pragma public, vary except encoding. We have expires header here, that is Friday 27th Jan. So we don't get the value as 60M, rather what we got is a date and time till which it should be cached. And as you can see, all these headers were not present in our previous request. The use case of caching could be more relevant for CSS file, JavaScript file, or JPG or PNG file which doesn't change quite frequently, and you might want to cache those resources for a longer time. As of now, we have just set it for one particular resource, that is python.png, but you can just do it for any other resource. So here in location part, you can set a regex expression telling that anything that matches with an extension .css, anything that matches with the extension CSS, JS, PNG, JPG should have all these headers attached to it. you can cache all these kind of resources for a particular duration. That's it for this lecture. See you in the next one. In this lecture, we are going to learn about compressed responses with gzip. So gzip is another directive in Nginx which can compress the resource before sending it to client. Now the question is, how does it help us to improve performance? The answer is, when a resource, for example a CSS file or JavaScript file, is sent from server to the client, if it is sent just like that without compression, then its size may be say 500 KB. So it will take 500 KB of bandwidth or maybe more depending on the headers. This will take some time to be transferred from server to client. This will eat up some latency and bandwidth on the network. But if the same file is being compressed by the server, then its size will get reduced, maybe somewhere around from 500 it will get reduced to say 300 KB. Then it will save that much amount of time and bandwidth. So the packets will be transferred much faster to the client. This way it will improve performance. So the gzip directive is added in the configuration file. So let us go back to our configuration file, which is the default configuration file. Here you can add under this server level, or you can also add it above the server level. If it is above the server level, it will get applied to all the server block that you have created, and if it is inside a specific server block, then it will get applied to that particular server block only. So all you need to do is you need to say gzip on, and this directive comes with Nginx core, so nothing to add explicitly. Next thing is to add gzip comp level. This is compression level that we want to have over the resource. I will set this value to 3. So this value ranges from 0 to 9, 0 being no compression at all and 9 being highest level of compression. That means if it is set to 9, the compression of the file will be maximum and the size of the file will be very low, and if the compression level is set to 1, then the file will be compressed less and its size will be bigger than the compression level of 9. You might be thinking of increasing the compression level to 9, but there could be an issue based on server resource. So the more compression that you are applying, it will require more resource to compress the file. So it is always better to keep some mid-level value, which is why I am taking 3, but you can also go for 4 or 5. So that's 3 to 6 is a decent range, but feel free to play around it. For now, we are going to go with gzip comp level to 3. Next directive is gzip types. This tells on what type of files we want to apply the compression to. It can take multiple values like text, CSS, or you can do it for text / JavaScript. You can also write it like this in a separate line. So you can say again gzip underscore types text / JavaScript. Now we have specified the gzip related directives. We need to understand one more thing here, which we talked in previous lecture about this header vary accept encoding. So a client can accept a compressed or non-compressed version of resource. If it is able to accept the compressed version, then it needs to send a header to the server saying that I can accept compressed response as well. So with this header from server side, we are essentially saying that the response from this server may vary, which is this keyword vary, may vary depending on the accept encoding. So if the client is able to accept gzip compression, the server will change the response and it will send the compressed version of resource. And if client is not sending that request header, and if client is not able to accept compressed version, then the server will respond with uncompressed version of resource. So this is what this header is meaning. So the meaning here is the response from the server will vary based on the client acceptance. So this is all that we need to put in. Now let us go ahead and save this file and let us reload nginx daemon. So let us reload nginx now. Now let us try to access style.css this time using curl. This time we are going to access sample.css, which is a sample file I have already placed. But this time we don't see any gzip compression because we have not specified that we are accepting the compressed response from the server. Now to tell to the server that we are willing to accept the compressed response, we need to do the same curl request, but this time with another option -h, which is for header, and we are going to say we are accept encoding and set it to gzip or deflate and simply make the request. So as you can see, we have got a content encoding response in gzip format. So our response is now compressed. We have simply shown the output of the headers from the server, but we haven't seen the compressed file yet. We are going to see the output, the non-compressed output first. So I'm going to access sample.css, but this time without -i flag, and will simply output the content. I'm hitting enter, and as you can see, this is the sample CSS, and you can say this is the normal content. Now we are going to again curl the same sample.css file, and this time we are going to specify the header accept encoding, and we are going to remove the -i flag, and we'll see the output. So as you can see, this is a binary output that we are getting, which is why it cannot be displayed in a terminal. So it is suggesting us to output the content to a file. So another way of checking is to download and save the output to a file and see their size. So we are going to download the uncompressed version first, and we will save the output to uncompressed sample.css. So we are going to first see the uncompressed result, and we are going to save this to uncompressed sample.css file, and then we are going to output the content of the compressed version to compressed sample.css file. Now we have both the file. I'm simply going to run du-sh star.css to see their file size. So as you can see, the uncompressed version is 96 KB, whereas the compressed version of this file is 8 KB. So you can see it has compressed a lot. So this way, compression can help you a lot to optimize performance for your application and web server. Hi, welcome to this lecture. In this video, we will see a hands-on on how to enable and configure HTTP2. HTTP2 is more of HTTPS because it requires SSL to be enabled, and it works only with HTTPS. I have Nginx installed through source code, so we will need to install the HTTP2 module and rebuild the Nginx installation. So let us go in the source code directory, run nginx-v, and copy this configure argument value. And to configure the HTTP2 module, run this /configure with the --help option and grab for http_v2. So that is the name, http2v2_module. Now let us use this runs /configure with the argument we just copied from previous output and append the http2v2 module. And as I said, it requires SSL also, so that module has already been added here with HTTP SSL module. Hit enter. Now compile using make command. Once that is complete, run make install. So we are done with this. Now we just need to restart Nginx. So before going with HTTP2, let us see what the web server is it configured with HTTP1 or HTTP2 presently. So let us quickly check that. Here is the default index.html file of Nginx. You need to go to developer tools, and in the network tab, select the index.html response. So right now there is no SSL. As you can see, it's plain HTTP request. And if you click on this, it will open up headers, and you can see version is HTTP 1.1. So it is currently using HTTP 1. So let's now enable HTTP 2 and we will check this again. So we require SSL to be enabled first as a requirement for HTTP 2. So we need to have SSL certificate in place. You can go for a valid SSL certificate issued through some certificate authority, or you can create a self-signed certificate as we are going to do now. So self-signed certificate is just for a demo. It is not recommended. If you want to get SSL certificates for free, you can use Let's Encrypt. But for now, we will use self-signed certificate for this demo. So let us make a directory with mkdir command inside etc nginx, and the directory name is SSL. This is where we are going to store the certificate. Let's generate these certificates using OpenSSL command line tool. Run the command OpenSSL request, that is req. So req is to request a certificate -x509. This is the certificate standard that we are requesting. -days, that means how long we want to make this certificate valid for. Let's make it 10 days for now. -nodes, which allows us to leave out the passphrase or password. -new key, which means generate a new private key. Then the type of the key, that is RSA, and the length of the key 2048 bytes. Writing the key with the option -key out, and the path is etc nginx ssl self.key, and -out option to write the certificate to, that is etc nginx ssl self.crt. .crt is the certificate file and .key is the private key file. Hit enter and the private key will get created, and it will ask certain questions like the country name, and it has to be provided in 2-letter code. These are not that really important in this case because this is just for a demo and a self-signed certificate. It will ask to provide all these details: country name, state or province, locality name, organization name, common name, email address. You can use the sample values as I am using, and then hit enter, and it will generate the certificates and key file for you. You can list the content using ls-l command. So these files have been generated. Now let us go ahead and enable SSL, that is HTTPS. In the nginx configuration file, change the listen directive from port 80 to 443 and add SSL. Now provide the path for SSL certificate using SSL_certificate, and then provide the path to the certificate, that is etc nginx ssl self.crt, and in combination with this, provide where to find the signing key using SSL_certificate_key, and then provide the path to the key, that is /etc nginx ssl self.key. So this is all for SSL. Now you can save this file, reload the nginx configuration, go back to the browser, change this to HTTPS and hit enter, and you can see this kind of warning because it's a self-signed certificate and browser will not trust this because this is not issued by a valid certificate authority. So you can just add exception and proceed. So now index.html is loaded over HTTPS, as you can see in the browser. In the network tab, if you select this index.html request and see the headers, it still shows HTTP1. So it's now time to enable HTTP2. So in front of SSL, just put HTTP2, save this file and reload nginx, and then reload index.html, and in the network tab, select the index.html file, and now you can see in the header section, it's now HTTP2. So this means the website is being served over HTTP2. So HTTP2 should be supported by all the modern browser, but even if it is not supported by a browser, then by default the web server will respond with HTTP1. So even if you are using HTTP2, you don't need to worry whether the browser supports HTTP1 or not. because it will send the response accordingly. So this is it for this lecture. See you in the next one. Hi, and welcome to this lecture. In this lecture, we are going to learn about fast CGI cache. As by its name, it's a cache. But what kind of a cache is it? So your web server may just not be serving static files like CSS, JavaScript or HTML file, but it may rely on a backend language like PHP, Python or any other language or its framework. In that case, the request from Nginx web server goes to PHP FPM and it processes the request, and it might interact with database and generates a final HTML output which will be given to Nginx, and then Nginx will serve it to the client. So the HTML format of the output received from PHP FPM can be stored by Nginx as a cache, and it is stored on disk. So next time if the same resource is being asked, it can be checked. If it is present, it can be fetched from that cache instead of going to PHP FPM again. This way, micro cache is helping us not to go to backend and avoiding unnecessary processing of the request, and instead we are getting the result from the cache. So this will help us to improve the speed a lot. So this micro cache is known as fast CGI cache. Now let us see. So here I already have a Linux server which is running PHP FPM, and it is also running Nginx, and we have fast CGI set in nginx.conf. So I'm just doing a cat on this file, and here is the output. So within this HTTP block, we have certain parameter related to fast CGI. Here we are enabling fast CGI. As I said, the cache is going to be on disk, so we need to specify the path where it will be cached. So fast CGI cache path needs to be specified, and here in this case we are specifying the path to be etc nginx cache folder. Next thing is levels. We have set it to 1:2. What it means is, to understand the levels, we need to go inside this directory and do a ls on this, and as you can see, the folder present here is single letter or single digit folder which is specified with this first digit. And if we go inside any of this folder, the number of letters will be 2. Let us go inside 1. So here you see the number of letters present here of 2 digits or 2 letters. So the level here means is, within this cache path, the name of the first folder will be of 1 digit or 1 letter, and inside that the name of the folder will be of 2 digit or 2 letters. Now how it is naming all these 05, 0b, this comes from a MD5 hash that we are going to just talk about. So these folder names are getting created by the cache entry that is going to get created. So a particular cache entry will get organized based on its last character. So if we go inside 1, so whatever the cache entry going to get created, it will pick up the last digit and will create a parent directory of it, and then it will take the next 2 digit or letter and will create the subdirectories inside it. So this is how the naming convention of these goes on. The next parameter is keys_zone, and here you need to specify name for this particular cache that we are creating, and we have given it a name PHP cache followed by a colon and the size of this cache. The size here we have mentioned is which is 100 MB, and this should be sufficient for most of the website. And the next entry is inactive, which is set to 60 minutes. So this parameter tells how long the cache entry to be kept in cache since last it was accessed. So this is all about the fast CGI cache path directive. The next important parameter is fast CGI _ cache _ key. This is how the cache key is going to get generated in the folders we have seen below. So here we specify how the key is going to look like. For example, the first thing is $scheme. Scheme is how the request was made, whether it was over HTTP or over HTTPS. Next is $request underscore method, that is get, post, put, delete, etc. Then we have $host, the name of the host, and then we have $request underscore URI, the resource URI that was requested. We can leave out scheme to have both HTTP and HTTPS. So once we have these fast CGI cache parameter set, we need to specify in location block the name of the fast CGI cache. So here I have an explicit file in nginx conf.d directory named imp.conf, and here in location block I need to specify the fast CGI cache name that I want to use. So here in fast CGI cache I am specifying PHP cache name. So this is the key zone that we have used and defined previously in nginx.conf file. So that was the parent file, and this is a child configuration file in which I have specified under a location block. So this is all for this lecture and how you can set fast CGI cache. This will definitely improve the performance of your website because it doesn't need to go back to backend, and backend doesn't need to do all the processing again. Instead, the nginx will be able to fetch the resource from cache. This is it for this lecture. See you in the next one. Hi, welcome to this lecture. In this video, we are going to see what server push is and how it can improve transfer of file between client and server. So this is the demo site that we have, and we have open index.html page. To see how is it getting loaded at the moment, open developer tools and go into network tab and reload the page. Disable the browser cache, reload and go to the network tab. So as you can see, we are getting three resources on this page: index.html, style.css and thumb.png. Index.html being the main resource. As you can see here, the browser is parsing the index.html and then it is finding the links to style.css and thumb.png, and from there it is trying to get those files. Both of them are being given by the server in a multiplex stream at the same time. So with server push, what we can do is we can transfer style.css and thumb.png along with index.html file. To demonstrate this, we will use a tool ng-http2. You can install this using apt command in Ubuntu. Run the command apt-get install ng-http2-client and hit enter. This is installed now. Run the command ng-http with option -n. This means we are not interested in the response. Y option to ignore the self-signed certificate, and S, which means print the response statistics. And this is what we are interested in. Paste the index.html URL and hit enter, and this will display the result. And as you can see, only index.html is downloaded. Run the same command again with an option A, meaning also request the linked assets with this request, and hit enter. And as you can see, this time it has downloaded not only index.html but also style.css and thumb.png file. You can see these two files were requested and downloaded at the same time, immediately after receiving index.html file. So with server push, what we want to achieve is we want to get style.css and thumb.png without appending this a flag in the command. So we will just request index.html and we should get the linked assets as well without using a option in this command. For this, let us go ahead and edit nginx conf file, add a new location for an exact match of index.html. Within this location block, add style.css and http2_push for thumb.png. So this means whenever /index.html is requested, the server should also push or send style.css and thumb.png together with the same response. Save this file and reload nginx. Now run the first test, but this time without a option. Hit enter, and as you can see, we have got both the files now. with this asterisk sign indicating that these were the result of server push. Also see the significant reduction in the process times and see the total time for these responses to be received. This has reduced significantly. Previously it was 964 and this time it is in 600 figures. So this is a much faster way of delivering the linked resources, and this will improve the overall performance for your application. So this is it for this lecture. Thank you. Hi. So far we have learned a lot of things about TCP or configuring your web server using some of the other tool. But the main question lies here: what all practice that you should follow while tuning, how much you should tune. So I have some guidelines that you should do while tuning the performance. So first of all, you should define certain metrics that you care about. For example, you want to improve speed, latency, or transaction per second. So if you have some metrics, you know what you are going to tune for, because some parameters can be used to tune X metric, whereas it can be harmful for Y metric. So it is really important that you should define certain metrics. Then once you have the metrics, define a clear aim. For example, I want to achieve this much of speed or this much transaction per second, and if you have reached at that point, you can stop tuning, because tuning could be a never-ending process. So it is really important to have a clear aim. Then configuration should be right and working before tuning. If it is not, then you might have to tune it again. Test with repeatable production data or production like workload, because your testing environment could be different. You might not have that much of production workload in testing environment. So tuning the parameters may behave differently in different environment. It is recommended to simulate production like workload. Take a record of every changes you make, and if it results just like we have done in one of our demo where we were testing the time taken to download a file before and after tuning a particular metric. So this way it will be helpful to know how much you are improving. So these are certain do's while tuning the performance. Hope you liked the video. Thank you. Hi. In this video we are going to discuss about ETH tool. So ETH tool is a command line tool which can be used to display or change Ethernet adapter settings. You can change network card speed, auto negotiation, wake on LAN setting, duplex mode, etc. using this tool. This will be helpful to identify difference in speed between NIC and different component causing performance issue. So let us try to understand the command and try to run it. So to display Ethernet interface details, you need to run ETH tool and the interface name. So this is my Linux machine. To get the name of the interface, run ifconfig, and as you can see it has ETH0. So run the command ifconfig to get the Ethernet interface name, and with ETH tool just specify that name and hit enter. ETH tool space the name of the interface, and this will show you all the details related to it: supported port, supported link mode, whether half or full duplex, whether it supports auto negotiation. So right now it is supporting auto negotiation. You can also disable it. You can advertise auto negotiation that this interface supports auto negotiation, the speed of this interface, and right now it's in duplex full mode. You get all these details using ETH tool, and then you can change all these settings using the same tool. Using this you can tweak the settings and see if it is working best for you and enhancing the performance. If you want to set auto negotiation of ETH tool -s ETH0 auto negotiation, this command will set it to off. Auto negotiation is the feature that allows a port on a switch router or server or any other device to communicate with the device on the other end of the link to determine the optimal duplex mode and speed of the connection. And the duplex here refers to how data flows on the interface. On a half duplex interface, data can only be transmitted or received at any given time. So you cannot simultaneously receive and send the data on a given link. In full duplex mode, you can send and receive the data simultaneously. Let us understand how auto negotiation works. When auto negotiation is enabled on a port, it does not automatically determine the configuration of the port on the other side of the Ethernet cable and then match it. So it is not automatically determining the configuration on the other side. So when auto negotiation is enabled, it is not doing that thing automatically. So this is a common misconception that often leads to some problems. To disable it, you can simply run eth tool -s eth0 auto neg off, and this will disable the auto negotiation. You can also set the speed with the command eth tool -s eth0 speed 100. You can set the duplex modes as well using the command eth tool -s eth0 duplex half. So this will set the half duplex mode. eth tool command settings can be set permanently with eth tool _ opt variable, and this can be set in the file /etc/sysconfig/network-scripts/ifcfg-eth0. Let us see this. So I'm just running it. I'm editing this file fcfg-eth0, and here you can add the option using the variable eth tool _ opts equals to, just provide the values you want, like auto negotiation off, setting duplex mode, whatever options you want to specify, you can just mention in this file, and this is it. Run the command eth tool -k eth0. It should be capital K. So there are a lot more things that you can do with eth tool. This is it for this video. See you in the next one. Hi, welcome to this lecture. In this video, we are going to talk about a tool that can help you for automatic performance tuning in Linux. The name of the tool is Tuned. You can install it on CentOS or RHEL based machines using the command yum install tuned. Or if you are on Ubuntu based system, you can use the command apt install tuned. So Tuned is a powerful daemon for dynamically auto-tuning your Linux server performance based on information it gathers from monitoring use of system component. Tuning system settings dynamically on the fly depending on system activity using tuning profiles. Tuning profiles include sysctl configs, disk elevator configs, transparent huge pages, power management option, maybe some custom scripts. By default, Tuned will not dynamically adjust system setting, but you can modify how Tuned daemon operate and allow it to dynamically alter settings based on system usage. You can use Tuned ADM command line tool to manage the daemon once it is running. So once it is installed, you will find the following important Tuned configuration file /etc/tuned. This is the Tuned configuration directory. And in this you will find tuned main.conf. This is the tuned main configuration file. Then you will have a directory /usr/lib/tuned. This will store a subdirectory for all your tuning profiles. To start the service, you can use command systemctl start tuned, and you can enable it by the command systemctl enable tuned. You can check its status by running the command systemctl status tuned, and if you want to stop the service, you can use systemctl stop tuned. You can control tuned using tuned ADM tool. There can be number of profiles, and to see which one is currently applied, you can run the command tuned-adm active. Here is the sample output. So as of now, the current active profile is virtual guest. To list all available tuning profiles, you need to run the command tuned-adm list, and this will list all your profiles like this. If you want to switch to any other available profile, for example, you want to switch to throughput performance, you need to run the command tuned-adm profile throughput performance, and then check if it is active or not using command tuned-adm active as shown in this screenshot. If you want to use the recommended profile on your system, run the following command tuned-adm recommend. You can disable all tuning by the command tuned-adm off. Hi, in this video we are going to create custom tuning profiles. So the tune tool comes with some default profiles, but if you want to have some custom tunings, you can do that by creating custom tuning profiles. To create a custom tuning profile, you need to go inside the directory /usr/lib/tuned. Here you can create a directory for your custom profile using the command mkdir I'm creating a directory with the name custom performance. Let's edit this file using Vim editor. So use the command vi custom-performance/tune.conf. Now put the following content in this file. Include equals to latency-performance, and summary. You can put some description like test profile that uses settings for latency performance tuning profile. Now save this and close it. To list this custom profile that we have just created, run the command tuned-adm list. As you can see, it has listed the custom profile that we have created. Now to apply this profile, we need to run the command tuned-adm profile and the name of the profile, that is custom-performance. So this is how you can create custom profile. And if you want to explore more about tuned, you can run the command main tuned or main tuned-adm. So this is all for this lecture. Hi, let us now deep dive more to understand the tool tuned. Let us list the profile using tuned-adm list command, and the current active profile is spin down disk. I want to activate server power save, so I will run the command tuned-adm profile server power save, and this is running some tunedm.sh script. Now let us see if it is active. So as of now, the server power save profile is active and it is applying some configuration in etc sysctl.conf. Let us understand what it is actually doing behind the scene by exploring the files of tuned. Let us go inside etc tuned profile, and here you have the directory server power save. So let us go inside this server power save, which is the active profile as of now. Let us go inside this, and it has certain file like ktune.sh, sysconfig and tune.conf. Tune.conf is the main file. Let us explore this file. It has a main section. This has a setting called interval equals to 10, that is 10 seconds. So this interval is for monitoring and tuning. Then this has another section called disk monitor, disk tuning, etc. So this is the main tune.conf, and main settings will be applied from here. Now let us see what is inside ktune.sysconfig. This particular variable use_ktune_d is set to yes. This simply means allowing it to use other files to use for settings. Let us see what elevator is currently used, and we will try to change it. So right now let us cat the file cat sys block sda q scheduler, and here as you can see the current elevator is set to cfq. Now we will try to change it using the tuning profile. So one way is you can run the command echo noop and write this to scheduler file, and as you can see the current active elevator is set to noop now. Or alternatively, if you want to persist this, you can edit the grub.conf file, and here in the kernel parameters you can add the elevator and set it to whatever you want, for example noop, but it will be set for always, and we don't want that. We want it to be active based on in order to optimize dynamically. So what we are going to do is we will edit the file ktune.sysconfig, and here we will set the elevator to deadline and elevator tune devs to /sda here, because I want to apply it to this particular disk, because as of now as you can see I am using sda and there are no other disk. So let us now apply this tuned adm profile server power save. Now this is getting applied. Okay, this is applied. Now let us see if we have the scheduler set to deadline or not. So as you can see it is set to deadline now, so our profile is working fine. So this is how you can apply custom configuration for tuning using tuned, and you can specify multiple parameters here. Even if it is related to sysctl parameters, you can change it dynamically using these profiles. So this is all for this lecture. Hi, in this video we will talk about some evergreen performance best practices. Regardless of the type of version of networking protocol you are using, all applications should always seek to eliminate or reduce unnecessary network latency and also minimize the number of transferred bytes. These two simple rules are the foundation for all of the evergreen best practices. So let us talk about these practices based on these two rules. First one is reduce DNS lookups. Every hostname resolution requires a network round trip. Whenever you are typing the domain in the browser, first that domain gets resolved. So there is a complete network round trip involved in that, which imposes latency on the request and blocking the request while the lookup is in progress. So if possible, try to make etc host entries when your application is talking internally with different databases server or maybe some internal application. This will reduce the DNS lookups and the application can find the IP of the domain from the etc host file present on the server where application is hosted. So this is gonna save you a lot of time and will improve application performance drastically. Next one is reuse TCP connections. We have also talked about it in previous videos, but this is one of the major and evergreen practice that you can follow. You can leverage connection keep alive whenever possible to eliminate the TCP handshake and slow start latency overhead. We have seen this in slow start video. So there are certain settings at web server level as well where you can specify keep alive so that whenever a connection is made, the web server will try to keep the connection alive for that particular duration. Next is minimize number of HTTP redirects. So HTTP redirect simply means you are trying to access xyz.com and at the web server handling the request for xyz.com, the web server again redirects that request to some other domain, say pqr.com. So whenever possible, try to reduce these kind of redirects. HTTP redirect imposes high latency overhead. Example, single redirect to a different origin can result in DNS, TCP, TLS and request response round trip. That can add hundreds to thousands of milliseconds of delay. The optimal number of redirect is 0. That means always try not to use HTTP redirects. Another one is reduce round trip times. Location of server is very important. Locating server closer to the user improves protocol performance by reducing round trip times. For example, faster TCP and TLS handshake will happen and it will improve the transfer throughput of static and dynamic content. Here you can make use of edge servers or some sort of CDN. Another one is eliminate unnecessary resources. So the thumb rule here is no request is faster than a request not made. That means if a request is not at all made, then it will be faster, right? So be vigilant about auditing and removing unnecessary resources. You might have added certain resources or certain images in the web page and later on you decided to use some other image. And now the first image is no more required, but it is still present in the code. And when the page renders in the browser, it makes a request for that image, but it is nowhere being used or displayed. Then it will cause unnecessary delays. So always eliminate unnecessary resources. So considering all these points, latency is the bottleneck and the fastest byte is the byte not sent. HTTP provides some additional mechanisms such as caching and compression as well as its set of version specific performance quirks. Another important best practice is cache resources on the client. So application resources should be cached to avoid re-requesting the same bytes each time the resources are required. Next is compress assets during transfer. Application resources should be transferred with the minimum number of bytes. Always apply the best compression method for each transferred asset. Eliminate unnecessary request byte. Reducing the transferred HTTP header data, example HTTP cookies, can save entire round trip of network latency. Another one is parallelize request and response processing. So request and response queuing latency both on client and server often goes unnoticed but contributes significantly and unnecessary latency delays. Another one is apply protocol specific optimization. For example, HTTP 1.x offers limited parallelism which requires that we bundle resources, split delivery across domains and more. By contrast, HTTP 2 performs best when single connection is used and HTTP 1.x specific optimizations are removed. So these were some evergreen best practices that you can always rely upon. Hi, we will be continuously improving the course by adding more contents and topics around performance optimization. However, we are open to your feedback. If you think some more topics around optimization should be included in the course, then feel free to suggest us and we will try to create more videos on it and will append to this course.